Welcome! Today I'll be showing you how to create your own NPC behavior trees using Behavior Tools for Unity, a package from the Unity Asset Store built on top of Unity's own Behavior Graph package that allows you to easily design and run NPC behaviors without writing a single line of code. To get started, we'll install Behavior Tools from the Asset Store. We can go to Windows, Package Manager, My Assets, and find Behavior Tools for Unity. We can click Download, and once it's finished downloading, we can import it into the project. Now it may ask you to install Package Manager dependencies. We can go ahead and just hit Install or Upgrade, as those are all free packages from the Unity registry provided by Unity itself. Once it's finished importing, we'll have this little pop-up asking us which files we would like to import from the package. We can go ahead for now and just import all of them. Once it's finished importing, we can come back to our scene, and I've already set up a basic scene here with an NPC character, a simple environment, and a nav mesh so the NPC knows where it is and isn't allowed to walk. I also have a simple enemy ready in my prefabs folder that the NPC character will later be able to chase and destroy. Now, to get started, we can create our first behavior graph. I'll make a folder for all of our behavior graphs down here at the bottom. And then we do create, behavior, and behavior graph. Now, I'm going to call this my NPC patrol and chase. We open that up and we get this new window here where we can see that we can press space or right click to add our first action. We also have over here the blackboard, which contains all of the variables our NPC will have access to, and the inspector, which can give us more information about any particular node in our graph, and there are often more options hidden in the inspector than appear directly on the node itself. So I'm going to go ahead and right click, add a new action, and I'm going to head down here to the navigation plus actions and pick patrol plus. So we can see here that we have an agent that wants to navigate along waypoints. Our agent will be the object itself that this behavior graph is attached to. And for our waypoints, let's create in the blackboard a list of game objects. And we'll call that waypoints. Now in the blackboard here, we want to make sure that this list is exposed, which allows us to set it in the inspector later. We'll then drag that list over to the waypoints option here. In the inspector here, we can see there are a few additional pieces of information here. We can decide how long it waits after reaching any given waypoint. Let's set that to 0 so that our agent is continually patrolling along the entire path. We'll also preserve the latest patrol point. That way, even if the agent moves along and goes off of its path to destroy an enemy, it will return back to the last waypoint it was moving towards. Our scene is set up in the XZ plane, so we can leave the navigation mode as is. For the speed, why don't we create a float variable in the blackboard so that we can control that and leave it exposed so we can control that in the inspector. I'll maybe set a default value of 5, but we can always change that later. We'll just drag the speed over to here. The distance threshold is how close the agent has to get to a waypoint to consider it being there. I'll create a variable for that as well, but leave it at the default 0.2. Now we don't have an animator here, so we don't have to worry too much about the animator speed parameter. The slowdown distance is the distance before it reaches a waypoint at which the agent begins to slow down. Since we want it moving continuously between waypoints, we're going to set that to 0. Finally, the desired velocity isn't something that we have to worry about for this, as we'll be allowing the agent to simply move through its nav mesh component. However, if you wanted to do custom movement through a rigid body, for example, then you can grab out the desired velocity and turn apply motion and rotation off to manually control the motion. We'll hook that up to the on start and we'll make sure that it's set to repeat. We can then right click and align all children to make our graph nice and neat. Now, this gives us a very, very simple graph. Let's head back to let's close that, head back to our scene, and on our NPC, we will add a new component, Behavior Agent. In the Behavior Agent, we can assign it a graph. Let's assign the NPC patrol and chase graph we created before. Now we can see we have self, the speed, the threshold, and the waypoints list here. So, let's set up our scene with a few waypoints for the agent to move between. I'll create an empty object here, call it waypoints, and then continue. We'll reset that to 0, 0, 0, and then create our waypoints underneath. Create a waypoint 1 here, and set it to the same position as the NPC, which is 0, 1, -3. And then I will duplicate that and place some additional waypoints around our scene. So there I've created 8 waypoints, which move in a sort of figure 8 shaped loop around the scene. Back in the NPC, we'll go ahead and assign those waypoints into the waypoint list here. With that done, let's run the game and see our NPC navigating between the waypoints. Now, it still seems that they wait very briefly at each waypoint. However, that's a fairly normal behavior. We can perhaps play around with the distance threshold. Increasing it allows the NPC to more smoothly move between waypoints, as it doesn't have to get as close to the waypoints before considering itself there and moving along to the next one. So I'll leave that distance threshold at approximately 0.8, and I think that speed of 5 is pretty good for now. Now, with the patrolling setup, let's create a behavior graph that can manage spawning our enemy prefab for the NPC to chase. So we'll call this the spawn enemy graph. And to start, we'll want a few blackboard variables, a game object for the prefab we wish to spawn, and a vector3 for the half extents of the spawn area, and we'll pick a random spot in that area. We'll leave both of those exposed and create a couple more exposed floats that represent the minimum time before a new spawn, which we'll set to 1 second, and a maximum time for a new spawn, which we'll set to 3 seconds for now, and we can change those later if we want. We'll then add an action from the delay category and wait for a range of seconds between our minimum spawn time and our maximum spawn time. We'll set that up under the onStart, and we'll align. Next, we want to cache the position of the object this graph is attached to, so that we can, and this does not need to be exposed, so that we can generate a random location around that position. So we'll go to the transform section and pick out the get position action, and we'll set that position to the position of self. From there, we don't want to set the y value, only the x and z. So let's grab a couple of individual floats for x and for z, which we, again, don't have to have exposed as we're just using them internally in this graph. And we can go to the math, vector, and component section to get the x value from the position, and then we can just search for the get z value to grab that one. Now, since we want it within the area of the spawn area, let's create two more float variables that represent the x and z of that area. Again, these don't have to be exposed as we'll just use them internally. Once again, we'll just get the x value, and this time it will be x area is the x value of the spawn area, and similarly, get z value, the z area is the z of the spawn area. So that gives us most of our basic information. So let's now create a couple of variables that represent the minimum and maximum for our random generation. Again, these do not need to be exposed. And what we can do is we can grab from the math section and primitive and basic an add and a subtract action. We can then set the minimum. We'll do just x first. We'll set the minimum to x. Actually, we'll set the minimum should be subtracted. So the minimum to x minus x area, and the maximum to x plus x area. We can combine those two nodes together. From there, we no longer need the x value itself, so let's reassign it to a random number. We'll go to action, random, and we'll pick random in a range. Now, it's already, since it internally uses min and max for the variable names, it's already automatically assigned to our min and max variable, but if it didn't do that for you, you can just drag them over as usual. And we'll set x to a random number between that minimum and maximum. Now, let's duplicate this entire block, and we can change all of the x values to z instead. So z minimum is z to z area, maximum is z plus z area, and then we set z to a random number between the minimum and the maximum. So that sets up, so far, our x and z now have the random values we want. Now, eventually we'll have to set the position of our new object. So let's put that into the position variable. We can just reuse the position variable for that in our, again, math and vector and component sections. We can set an x value and set a y value. So let's set position's x value to x, and then we'll set y or z as well, and we'll set the position's Z value to the newly randomized Z. We'll hook that up. Now, with both of those set, all we have to do is go to our game object actions, and we can instantiate a new game object. Now, we do want to be careful about the options in the inspector here. You can see here, we can specify the object we want to spawn. That's the prefab. Now, we don't want this to run in the background because we want to, as soon as it's finished spawning, set its position. We'll set that to false. Now, we need an instantiated object to store the newly spawned prefab. So we'll create a new game object. This is our new enemy. It should not be exposed, and we'll assign that to this instantiated object field in the inspector. We can hook this up, and then the final thing we need to do is simply go to transform and set position, and we will set the new enemy's position to our newly randomized position. We can then head back up to the top if we want and align all of the children so that the graph is all nicely spaced out. We'll then close that, head back to our scene, create a new object, which we will call this the enemy spawner. We should probably place this right around the center of the map, similar to where the NPC itself is, which is at 0, 1, and -3. So we'll place it at 0, 1, and -3. We will add a behavior agent and attach the spawn enemy behavior graph. Now, we need to give it the prefab, so let's go to our prefabs folder and drag in our enemy prefab. We'll leave this spawn time. Now, to set the spawn area, rather than doing this manually, let's use one of the behavior gizmos that comes with behavior tools. We'll add another component and we'll search for the cube behavior gizmo. If we add that, we can now see this red cube area. Now, we need to tell with this we can create a half extents that covers the area we want, and we only here have to really worry about the X and the Z values. And we'll make sure that gizmo looks good. Looks like it's leaning into the wall a little bit at the end, so we maybe need to bring the object itself forward a little bit, and then make that Z a little bit smaller. Maybe a Z of 6 and an X of 10. A little bit more forward. Yeah, there we go. Now, we can get this half extents to automatically sync with the spawn area here with just a few steps. First, we have to tell it what behavior agent it's syncing with. So it's just syncing with itself. Then we have to tell it what variable to sync with. That will be the spawn area. Finally, if we set should sync equal to true, you'll see it has automatically updated the values in the behavior agent to match the values in the gizmo. If we make changes here, it makes changes directly in the behavior agent itself, and vice versa as well. Which makes it very easy to visually design our behaviors. If we try this now, we should hopefully see an enemy spawning every 1 to 3 seconds. There's one now, and there's another, and they'll keep spawning through the game. So with our enemy spawning all set up, let's now get the NPC to chase after and destroy the enemies. We'll go back to our behavior graphs and the NPC patrol and chase graph. We can move these existing nodes over to the right a little bit and add a sticky note that says these move the NPC. We can then add another onStart event, and these onStart event trees will happen in parallel to each other. We'll add a sticky note saying this onStart tree to the left is responsible for detecting enemies. We'll have it search in a sphere around itself, so we'll go to Actions, Object Detection, Physics 3D, and Overlap Sphere. We'll have Self detect objects, so we need a new game object list. We could create that in the blackboard or right from this link variable here, which will create it from in the blackboard for us. Let's call this possible targets. Now, it does that in a sphere with a radius. Let's create a float variable for that radius and call it detection radius. Now, the possible targets don't have to be exposed, but the detection radius should be. Now, selecting the node again, we can go over to its inspector, and we can see that we have several options in here. To keep it simple, we won't do anything with layers today, but to make sure the agent isn't detecting itself or anything in the environment, let's set it up to use a tag, and we'll tell it to search for the enemy tag. Also, just in case, let's have it return the rigid body of anything it detects rather than the colliders. We will temporarily go back to our code and make sure that our enemy prefab is set up with that tag. So we'll add a new tag. We'll call it enemy. We'll save that tag. Go back to the enemy prefab and make sure the tag is assigned. Now going back to our graph, we can hook this up, and then that gives us a list of all the possible targets. So let's have the agent just go for whatever target is closest to it. So going again to Action, Object Detection, and filtering this time, we will get closest to agent from list. We need a new game object variable to store the target itself, which does not have to be exposed. It is a member of the possible targets list, and it is closest to self. Now, you could do a more complicated thing, such as checking that the target is actually visible to the agent, or looping through all of the different targets. For now, we'll keep it simple and just do this. However, repeatedly running sphere casts every single frame is a little bit inefficient. So what we'll do is we'll add a small delay. And you could set a specific delay, but I like to set a range of delays simply because from something like 0.19 to 0.21 seconds, simply because if you have multiple NPCs running the same graph, having this randomness ensures that their detection happens on different frames, thus reducing any lag spikes. We can align all of those up, and that's it for a very simple detection. Now, over with the movement, we're actually going to break this connection here, and we'll add another navigation action. We'll go to Navigation Plus, and we will navigate to target. Agent will navigate to the target that we've selected here. Now, this navigate to target action automatically fails if there is no target, if target is null. Therefore, what we can do is we can go to the flow nodes and at the very bottom, try in order. Now, it will try in order from left to right, so we'll assign both of our different navigation nodes as childs of this try in order. So it will first try to navigate to the target if there is one. If there isn't, it will fail and head over to moving along the waypoints once again. Now, in the Navigate to Target inspector, let's make sure all of these are set up correctly. Closest point on any collider should be fine. We do want the agent to be self. We are moving in the XZ plane. However, our speed should be set to the speed variable we created earlier. And the distance threshold, let's also set to be the same as it was for our waypoints. and the slowdown distance should be 0. We do want to apply motion and rotation. Now, with all of that set up, this action will continue moving the agent until it reaches the target. Once it does reach the target, let's have the agent automatically delete the target. So, we'll go to Actions, Game Object, and Destroy Object, and simply destroy the target. Now, the last thing we need to make this move logic work properly is we need to automatically restart this entire tree if the target has changed. For example, if a new one has been detected, or we've reached the target and it has been destroyed, we should restart the whole logic of how it decides how it's moving. So, we will add a flow action. In abort, we can add a restart node. We will restart if, and we will assign a condition. Under variable conditions, we can say variable value changed and assign the variable to target. So whenever target changes, even to or away from null, then this whole tree will automatically restart itself. With all of that set up, let's head back to Unity. We'll go to our NPC, and just like we used a Behavior Gizmo to set up the area where the enemies spawn, let's create a Behavior Gizmo, specifically a Sphere Behavior Gizmo, to control the detection radius for the NPC. The agent it operates on is the NPC itself. The variable is the detection radius, and we do want that to sync. Now we can increase this value from either the behavior agent itself or from the gizmo to see how big that detection radius is. I think a number around 3.5 looks decent, covers that entire area in the middle. So with that all set up, let's run the game and take a look at our NPC navigating around and destroying enemies. So you can see there, it went off of its path when it detected that enemy, and then it goes right back on. That's it for this video. If you haven't already gotten behavior tools for Unity for yourself, there's a link to the asset store page in the description below. I look forward to seeing what type of NPC behaviors you can design for yourself.